we'll start the recording. So welcome back, happy Thursday. I have some fun new things for everyone to do. Just in case you were bored and had nothing to do but watch television, I decided to swoop in and save you. So I sent out an email yesterday announcing the availability of two new things. One is a formative assessment. So that is inside icon under quizzes, the usual deal. Answer as best you can. Try to do it from memory, but it's fine to consult your notes. Get your 2 points for giving it a shot. Half a point off if you're late, and we'll go over it the next day. Otherwise, I also put up a new homework, and related to that, I have a couple of things that I wanted to point out. So it is a homework over counts. So you're going to be predicting the number of new foods tried amongst preschool students. And like all of my homeworks, this one is based on a true story. So while I made this homework, what was happening in our world 2 years ago, pre-pandemic, was that my son was attending food school. So in the homework, I made this up. It's based on a real thing. It was a desensitization program where he was working with an occupational therapist to sort of get over his fear of new foods. And it was going well, and he was learning. And then the pandemic hit, and we had to shut it down. And so, unfortunately, since then, he will still only eat like 5 different things on the planet Earth and freaks out if you try to give him anything that's not exactly those 5 things. So not a great happy ending to the food school thing, but it's still going. I realized as I was putting it together that even though the multivariate wald test that I built example 3 out of worked perfectly in R, they did not work perfectly in the homework. I realized that as I was testing it. So what you don't know is on behind the scenes, in order to remove a question and reorder everything that follows is a tremendous amount of work because everything is like tied to the exact question number. So you will see that I punted and asked a couple of very easy questions just so I wouldn't have to renumber the entire homework. So there's no wald tests, so everything should agree. The other thing that I had to fix to make sure that everything should agree across the 3 programs was, and let me get my screen share going here so I can get everybody on the same page, in example 3. So this is example 3 where we introduced a log link and a Poisson distribution, which you'll be using in your homework. And in Stata is the one that the Pearson chi-square over degrees of freedom was different between SAS and Stata because of the denominator. I figured out how to fix it. So in example 3, I inserted this little piece of code in the handout as well as in the example files online so that you can use this to use the stored results in Stata. So this is the Pearson chi-square total, and then you can divide by sample size as stored rather than sample size minus degrees of freedom. So for those of you who are using Stata, the answer to the questions about Pearson chi-square can be found with this little piece of code. So then everything should work out the same way. So you'll get a chance to practice doing Poisson and negative binomial models as well as likelihood ratio tests in predicting the count of number of new foods tried in this fictitious story. The other piece of it that is referenced in the instructions, so let me pull up one more thing that I forgot, is I am asking you to fit a piecewise slope model for the effect of food school. And I had warned you at the beginning of the semester that this was coming. This is the homework that it's in. I believe it's slide 7, nope, just past it, this one. So there's a reference to this slide in the instructions for your homework because this is an example that will help you do the coding for separating the effects of food school into whether or not they went and then how many sessions if they went. So it will look remarkably similar to this example. So a count variable essentially for a predictor and a count variable for the outcome at the same time, and fun with linear models in this one. So this is not due for a week and a half though. I just wanted to give anyone a head start to get a chance to work on it. So let me know if anything goes wrong or if you have any questions as you get working on that. Okay, so any logistics questions, homework questions, anything like that to start with? No? Am I frozen? No? Okay, everyone's just really still on my camera here. Sometimes it's hard to tell. All right, then I will shut that down. And we can finish with Unit 4 in sort of the first half of the class. Caitlin says, I am coming in and out a little, but not frozen. Okay, well, let's see. Nothing extra is running. Let me shut off Dropbox. Sometimes that's a memory hog. Give it a minute to catch up. Okay, is that any better? Maybe it's the sleet. Mother Nature doesn't want to have us have class today. Should have just taken it as a sign. All right, well, Zoomers, let me know if you have issues with hearing me or if I get frozen. Sometimes it's hard to tell. All right, then where we were last time is looking at binomials and beta binomials. So let's start back in example 4a to finish that up, and then we'll change gears to example 4b. So I am on page 9 of example 4a. Just to do a little bit of reviewing, the story here is that we are predicting proportion correct in a distribution where like 45% of the kids got 100%, so it's very skewed, and potentially what I would call one inflated, not zero inflated, but one inflated. So I'm trying out basically a combination of 4 separate models that you can think of as a 2x2 combination. So whether or not the amount part, how do I say this? The proportion part that is continuous, whether that follows a binomial versus a beta binomial, is one distinction, where a binomial is a distribution that does not have a separate parameter for variability. So it's supposed to be a function of the mean only, just like it is in Poisson. That is not going to be adequate for our variable, though, because of the excessive skewness that we have coming off of that ceiling effect. So I'm trying an alternative, which is known as beta binomial, which adds a scaling factor that allows the variance to exceed the mean, but it's a multiplicative scaling factor. So it works similarly to negative binomial. So binomial versus beta binomial is one dimension. The other dimension that we started looking at last time was zero inflated or not. And in this case, the problem is not zeros, but ones. But because I couldn't find one inflation as an option within the software packages, I decided to flip it so that we're predicting number incorrect instead of number correct, so that we can use zero inflation software to be able to model it. So those 4 possibilities to look at. And I think we've done most of it, but I figure it wouldn't hurt to remind us of where we were. Am I right on that? Never hurts to review? Yeah, as a general rule, I think that's true. So any questions on the setup or any of the models before we jump back into what it looks like in the results? No? Cool. All right, rock and roll. So to do these models, I am using different packages in SAS and in Stata, actually. So proc finite mixture model is where I found these choices. So beta binomial is one of the built-in distributions there. So this model is predicting number correct still with my 2 predictors. And in order to test whether or not beta binomial is an improvement over binomial, I can do a likelihood ratio test. So generally speaking, cough, cough, homework questions. When you add a parameter to a model and you do a likelihood ratio test, if the test is significant, that means the parameter that you added helps the model fit better. So it's an improvement. If you add something and the test is not significant, that means it is not an improvement. Not that it's worse, it's just it's not better. So if you add something and it doesn't help, then you could use it, but you don't have to. If you add something and it does help, then you probably should use it. So I am showing you how I would go about this process of building a likelihood ratio test myself using SAS. I also have Excel spreadsheets that can do this because it's the chi-dist function in Excel. Gives you an exact p-value for any value of chi-square. In this case, I don't have to go to the trouble to do this because I can just eyeball the numbers. So the -2 log likelihood value for the model that just had a binary conditional distribution was 1,531. The minus 2 log likelihood for the version that has beta binomial instead is 531. So those two numbers, the critical value for comparing them with a mixture chi-square is 2.7, and they're different by like 1,000. So we know what's going to happen, but I wanted to give you the code to be able to do this. So I'm computing a test statistic, which is the difference in minus 2 log likelihood, a degrees of freedom for the test, which is the number of parameters by which they differ, then getting a p-value, which uses the prob-chi function in SAS. Each program has this built in. And then the mixture version is taking that p-value and multiplying it by 0.5. So 0.5 of a chi-square distribution with degrees of freedom 1, and then 0.5 of a chi-square distribution with degrees of freedom 0, which doesn't exist, and so that's 0. So it works out that in this case, you can cut your p-value in half, and it fits a mixture distribution. And then I asked it to print the p-value using a format for p-value so that it would look the usual way. Okay. And then I did outputted predicted proportion correct and correlated it with the real one so that I could get some kind of R-square type approximation. In Stata, I am using a custom package written by somebody. I don't remember who, but I think it might be the people from your textbook. So Stata has a lot of people who have contributed to it in the same way that people write R packages. This is called beta bin, and it looks pretty much the same. So all of Stata's packages are structured with the same type of language. In Stata, what I did is compute a test statistic by manually typing in the minus 2 log likelihood values. I tried for like an hour to get it to work in Stata with just it remembering the values, and I couldn't do it. So I just had to give up and type the numbers in myself. If anyone figures out how to do this without having to type the numbers in, please tell me. I will be eternally grateful. But this is also more transparent potentially too. The chi2 function gives the probability that corresponds to that chi-square value, and then I cut it in half to make the mixture version. So same idea. And then the predict function gives you the predicted proportion correct. I correlated it with the real one and then squared that internal correlation. So this thing right here remembers what the correlation was, so I can square it and print it. Okay, any questions from SAS folks or Stata folks about likelihood ratio tests? So this process, by the way, this likelihood ratio test difference in minus 2 log likelihood, this shows up all over the place in statistics. So when we do multivariate models in the next unit, and we try to compare alternative models for the patterns of variance and covariance across outcomes, this shows up. When we're doing structural equation modeling and we want to see whether or not our model fits, that's a likelihood ratio test against the best possible model. In item response theory, if you want to know if you can get by with a 1PL versus a 2PL, that's a likelihood ratio test. So it shows up everywhere, this general thing. It goes by a lot of different names. Sometimes it's just called a chi-square test. Sometimes it's called a deviance test. But since it is based on likelihoods, I think the easiest way to describe it across disciplines would be likelihood ratio test, which corresponds to differences in log likelihoods. So this is useful, one point being, this general idea shows up everywhere. All right, in R, then we are, let's see here, we are doing this. That's what we are doing. So I calculated that myself. So minus 2 times the log likelihood. By the way, in your homework, R users, this is what you're going to have to type to get the minus 2 log likelihood, this little function. It doesn't get spit out automatically in the GLM package. So I have that in the example, but just to remind you that that is the case. So I am computing the difference in the two log likelihoods, then multiplying it by minus 2. Order of operations doesn't matter. You can do it either way. And then here is p chi-square gives me the p-value. Cut it in half to get the mixture version. And then using the predict function to compute a column of predicted proportion corrects, then correlate it with the real one. So we end up with this new term right here that corresponds to the beta binomial. And that new term is given in a couple different ways depending on which software program you're in. In Stata, it gives you the 1 over that term plus the log of that term. And in R, it gives you 1 over that term as well. So you have to do a little bit of detective work to figure out exactly what it is. But even if you don't necessarily know what to do with these additional scale factors, we can test whether or not they're useful, and that's where likelihood ratio test comes in. So in this case, the difference between -2 log likelihoods is like 1,000. So yes, adding whatever the scale factor is that allows the variance to exceed the mean helps the model fit much, much, much better. And then here is the version in R where they labeled it as an intercept, which it absolutely is not. It is the log over 1 over the scale factor is what it actually ends up being there. Then we get into the zero inflation models. So we talked about this a little bit last time, right? Maybe? Maybe a little bit? So the reason that I'm doing zero inflation is because I can't do 1 inflation. So this is a hack. But as we discussed last time, if I fit a model that predicts proportion correct, I can also anticipate what the model would look like if it were to predict proportion incorrect instead. It is literally just flipping the signs, because what we're doing here is logits. And if the logit of a right answer, say, is a 2, then the logit of a wrong answer is a -2. So if the logits predicting proportion correct are positive, I multiply them by -1 and I get predicting proportion incorrect instead. So logits work that way, no matter what kind of outcome we're predicting, if you're in a logit link. So I'm going back to a straight binomial model and asking whether or not I need a separate submodel for the probability of being an extra 0. So I'm predicting number incorrect so that I can do it this way. And I'm just putting an intercept in, no predictors in the zero inflation submodel at this point, just to see if it helps to have one. So can I just predict number incorrect, period, or do I need to do that plus zero inflation? So in SAS, it's back to binomial for a moment, and then here is the zero inflation submodel. I could not figure out a way, by the way, to add predictors to it. So it looks like it just allows it to be there, but within this particular routine, it doesn't let me add any predictors. I'm again doing a likelihood ratio test, and so note the 2 models that I'm comparing at this step is binomial versus zero inflated binomial, because I'm adding a submodel that creates the addition. So these are nested models where binomial is the baseline, and then adding a second submodel to predict zero inflation, test whether or not that helps. And again, I can look at the -2 log likelihood values and say, yes, it's going to help. In Stata, I'm switching to another user-defined package called ZIB, so zero inflated binomial. I am adding 2 things with respect to that here. iLink is what link function I want for the inflation model, so that's what the I stands for. And then the inflate tells it what to put as the linear predictor for the inflation model, and I just want an intercept. So I'm leaving that alone for right now. And as I discussed last time, honestly don't know what all this stuff in R is. I just know that in the example I found, this is what made it work. So I'm being honest, right? I can't know everything. I learned this 10 minutes ago and I'm trying to teach it. So this is what I got. I can tell you that this, I think, corresponds to the primary model. And this must correspond to the inflation model because that's an extra thing. And I don't know what this stuff does, but without it, it didn't work. So I'll have to keep working on that. Maybe I'll get it right a year from now when I teach the class again. Yes, Kaylin says, I appreciate the honesty and I feel stupid. I feel stupid every single day. I'm not even exaggerating. So for those of you who are looking forward to a career in academia, just get it through your head that you are never going to feel like you're doing enough, you're productive enough, you know enough. And all I can say is just channel your inner Stuart Smalley. Am I old enough? Anyone know that reference? Okay, ask the YouTube after class, not right now, but after class, for Saturday Night Live, Stuart Smalley from the 90s. It was a character who was like a self-affirming sort of counseling type person, and he used to end all of his bits with, because I'm good enough, I'm smart enough, and gosh darn it, people like me. So you just have to say that to yourself every single day in the mirror if you want a career in academia, because otherwise it becomes overwhelming. But yeah, I'm not going to stand up here and pretend like I know more than I do. But at least I can do this much. I can make R do my bidding today. Maybe not next week, but for today I can make it work. So, anywho. I can make it work with the likelihood ratio test. Again, so yay for that as much. Here's what I get back. So in SAS, it doesn't do the work for me to divide the Pearson chi-square by degrees of freedom, so I did that myself. So it works out to be 2.3. So it's better than it was for straight binomial, not as good as it was for beta binomial, so it's somewhere in between right now. This thing is what's known as a mixture model. And mixture models, generally speaking, can be used either badly to find hidden groups because they are exploratory procedures, or they can be used to approximate a non-normal distribution with components to it, which is the latter is the case of what we're trying to do here. So it gives me listing for component 1. So this is the binomial part of my standard model. So this is giving me the logit of the probability of any one trial being incorrect at this point for my reference child who has non-specific language impairment and whose mother graduated high school. So component 1 is how it's labeling it as what I would call submodel 1. Then the mixing probabilities here, it's telling me what the probability is and then the corresponding logit for the second submodel. So what is the logit of being an extra 0? It is minus 0.35. That corresponds to a probability of being an extra 0 of 0.41. So in this analysis, it looks like because the binomial distribution does not do a very good job of capturing the zeros, it thinks that 41% of my sample is an extra 0. That's pretty high. Now, whether that's good enough would depend on what happens after I add the beta binomial component to it. But for now, it looks like, yeah, this definitely helps relative to just straight binomial. Same thing down here in Stata. The submodel for zero inflation is labeled as such. So we've got the logit of the probability of being an extra 0, as well as the rest of the standard submodel predicting the number incorrect, the probability of any one trial being incorrect. It gives me this, which is nice. That's my likelihood ratio test against a regular binomial model. So whoever wrote this package anticipated that one might want to do that and did it for you, which is always good. Or wait, nope, I take that back. That's me. I did that. Again, my head is in the handout that you'll see next week. I forgot what I did in this one. I did that because otherwise I wouldn't have gone to the trouble to write all this part. I did that. So whoever made Zibin, maybe you could work on that, okay? Or ZIB and ZIBB is next. Where'd R go? Here we are. Here's R. Intercept 2 is the logit of the probability of being an extra 0. So, oh wait, no, I take that back. I made a note here. Just for fun, R predicts the logit of the probability of not being an extra 0. Just for fun. Because look, it's a positive 0.35. The other packages return the negative. That's how I know which it is. So I think, Farhan, is he here? He's not here today. So last time you asked, what do you do if R doesn't give you the right answer? Run something in another package and then see if you can figure out how it must be off. because I don't know what the right answer is in these data. But what I can tell is what's happening across the packages and try to make sense. In practice, I will tell you, learning how to simulate data, even in situations where you don't need to, can help you figure out what software is doing. So that is something that I tend to do quite a bit when I'm learning a new model or something, or a new routine, is make up data where I know what the answer should be and see if it comes back. See if it comes back as the inverse or the reciprocal or some mess with it, then I know what it is. So learning how to simulate data can help you figure things out in situations where you don't know what the answer should be. Okay, so recapping so far what we have. Binomial by itself, not nearly good enough. Beta binomial, much better. Binomial with zero inflation, better than straight up binomial, but now we need the fourth one. So zero inflation and beta binomial altogether. So that's number 6 here. So I can do that in SAS with dist equals beta binomial plus this empty zero inflation model. Doing my likelihood ratio test, it's going to fit much, much better. In Stata, it's ZIBBIN, so zero inflated beta binomial, still with an empty zero inflation model. And here's honesty in writing. Could not find zero inflated binomial beta regression in R, so I give up. I gave up. I couldn't. At some point, you just got to be like, I can't do it. I'm sorry. So you don't have a homework on this. If anyone can figure this shit out, please let me know. But I'm good enough, I'm smart enough, and gosh darn it, people like me. All right, so the answer then to this model, according to Pearson chi-square over degrees of freedom, that's 0.87. So just a scotch under, but much better than anything else that we've seen. And I will say that relative to the original version of the model without zero inflation, the scale factor is much bigger. So once you take off the pile of zeros, it looks like the variance needs to stretch even more. So the zeros were kind of bringing it down. The mixing probability, it's only 25% extra zeros in this case. So it looks like so far this is our best fitting model relative to this, as well as relative to all the likelihood ratio tests against the next nested models. And it yields an R-square for the correlation of predicted proportion incorrect and actual proportion incorrect of about 0.15. So not bad. So then here's the output from Zibin. And one more bonus model, just because I could figure this one out. In Stata, it does let you add predictors to the zero inflated model. So I'm doing Zibin right here, and then adding in my predictors. So now there are a total of 4 slopes in my model. Group and Mother's Education are predicting number incorrect, including the zeros that are part of an expected beta binomial for number incorrect. And those 2 same predictors are also predicting the logit of the probability of being an extra zero. Survey says neither of them are significant, so we probably don't need to keep them. So then at this point, because my head hurt, I had to make a table to figure out what's what and compare everything. So when possible, I did -2 log likelihood comparisons for nested models. So regular binomial is nested within the binomial that has a random intercept for added over dispersion. So obviously this one fits much better. It's also nested in the beta binomial that adds the multiplicative scale factor. Regular binomial is also nested in zero inflated binomial, which fits much better. And then these 2 are also nested because they're both zero inflated. The question is, for the amount part, is it binomial or beta binomial? So by all of these sort of, nesting standards, this one looks like it's the best. But the addition of adding predictors makes the minus 2 log likelihood AIC and BIC a little bit higher, which is bad. So actually these two are higher, this one's lower because it always has to be lower when you're adding predictors, but I don't know how well it fits because Zibin didn't give that to me. So that's why across all the alternatives, I chose that one. And then here's my attempt at a write-up that translates all of that. Okay, so that's the end of the story. Any questions?
Not a question, but a comment.
Comments, welcome too.
So I was traveling the past few days, and I told some people this already. I was on a plane. It was there's a lot of turbulence because there was a huge storm yesterday.
Sounds fun.
And so I downloaded the class and listened to it like a podcast, and it helped, soothe me as I was tossing through, all the turbulence.
Well, I'm glad.
So, an indirect thank you.
You're indirectly welcome. Maybe I should adopt a podcast voice, you're listening to Lisa Hoffman's Stat Channel. Thank you for joining us. Something sort of who is it? Delilah, the radio host.
Yeah.
Like one of those voices. Not like the crazy hyper version of me, after 3 cups of coffee, which is what y'all get right now. But the toned down version. I could work on that. Or I could do this in my mommy voice. There's that one too, right? Okay, so what I'm gonna need you to do, no, Huey, no, come here, no, listen to mommy, please. Okay, now we need to do the beta binomial. No, not the binomial, the beta binomial, okay? Yes, I know Luigi is very big, and Bowser is very scary, but can we focus on this? Okay. So, then you can get that version. Anywho, I'm glad that I helped you overcome turbulence. It's my pleasure. All right, any other questions or comments before I shut this one down? Okay, bye-bye. Okay, we're almost through this, the rest of the continuous outcomes. So the very last thing, then, that I have in this unit right here for slide 10, lecture 4. Other kinds of not normal outcomes that we haven't talked about yet. So we're still in the version of generalized models, things that are not normal, but that are continuous. So here's the deal. If you have, say, a count variable, you can pretend that that's continuous. All software will let you do that. It doesn't know or care that you're missing decimal values in between the integers. But the reverse is not true. So if you have a variable that's response time in milliseconds, where you divide it by, say, 1,000 so that it's response time per seconds, and you try to fit a Poisson model or something to that, it won't let you because you don't just have integers. So if you have continuous data, then you do have to pick distributions that are for continuous data. Now, the only one that prior to teaching these models I had ever heard of was normal. But there's 2 others that I've seen used for this purpose, and one of them actually simplifies to just being a data transformation. So we're talking about outcomes that are continuous, but that are sufficiently skewed and may not have zeros to them, and what to do in that case. So in all of these instances, we're going to use the log as our way of dealing with the boundary at 0. So things like house prices, response times, anything where you can't possibly have a 0. We can either do a log normal conditional distribution or a gamma distribution. Neither of these have zeros in them, so they're only for positive values. If you have 0 values also, then you would have to add a second submodel when it would be like hurdle, except it's known as 2-part. So I want to show you a couple examples with these sorts of models, and then also point you towards something that I feel like is useful, but isn't technically a generalized linear model, which is quantile regression. So we'll do that one last. Question?
So, are there any cases where it could, via outcome could either be continuous or categorical depending on how you interpret it. Like, I'm thinking Likert scales, just kind of depends on the situation, or, I mean, I guess a little bit. Do you know what I'm getting at?
I think so. So proportion correct is what we just modeled.
Mm-hmm.
That's continuous, but bounded, right?
Yeah.
Like it goes between 0 and 1, but it can be any number. I turned it into a discrete variable so that I could fit these binomial routines to it by modeling number correct and then add a number of trials.
Okay.
So from that perspective, yes, you can sort of finesse things, but there are certain types of variables like response time in milliseconds or something that's never going to be discrete.
Yeah.
You'd have to round it into bins of some kind, and generally speaking, you do not want to do that to continuous data. So these are instances in which, like minutes of activity per day, that's a common type of thing. Anything involving money, salaries, blood pressure, rates of whatever, like these are the sorts of variables that we're talking about.
What if it's continuous, but they're on different scales, and you want to retain the continuousness of it without putting it into categories?
You'd have to give me an example of what you mean by that.
So I was looking at a project with one of my friends, and he had like scales, but to rate like it was like an academic test, but one scale he wanted to compare tests together, and one scale is out of 20, one scale is out of like 150.
Oh.
So what would be the best approach in that case?
If you want to make a comparison, you'd have to put them on the same scale.
Okay.
If you wanted to treat them both as outcomes, you could fit a multivariate model to predict both simultaneously.
Okay.
And any kind of latent variable model, by the way, you can have items that are on different scales. So if you wanted to build a survey and some of your questions were best asked as binary questions, like do you do this or not, or do you have this or not, and some of them were best asked as 3-point questions, and some of them were best as 5-point, you can totally put them all together into one model for one trait. Actually, they don't all have to be the same.
It's Kwangman. I think he actually talked to you about this at one point.
Maybe.
But yeah, that's because we were trying to figure that out, and I thought, would standardizing be a good option or not so much?
That would be your only choice if you're trying to put them into where a 1 unit something means the same thing.
Yeah.
You'd have to convert them into some kind of similar metric.
Okay.
But you don't always necessarily need them to be on similar metrics. It depends on what you're doing with them that matters. So, but we're talking in this case then about continuous variables that aren't normal. That's our goal here. So here's log normal. And this one is special, because this is the only instance that I know of. So what you would be doing in this case is fitting an identity link, so not doing anything to the link function, and saying that the residuals follow a log normal distribution instead of regular normal. That's an option. And that works out to be exactly the same thing as just logging the outcome and putting it in a regular linear regression. So in situations where a generalized model would not be desirable, so multivariate data, repeated measures data where you don't have a lot of people, you would be stuck using regular flavor maximum likelihood, which means that your variances would be potentially downwardly biased because of that. If I want to use residual maximum likelihood to get better estimates of random effect variances, but I've got a variable that looks skewed, I'll take the log of it and throw it into a regular old multi-level model. So this is perhaps one of the reasons that people who do research studies involving reaction time or response time often just take the log of that variable and stick it in the model, because it works out to be the same thing as saying you're assuming that the residuals have a log normal distribution. But there's no link function, so you don't have to worry about the weirdness of the average of the logs not being the same thing as the log of the averages, because the link is identity. So a log normal distribution would be any of these, and you can see that they address the skewness reasonably well, and log normal is a distribution that doesn't have zeros in it. It's all positive numbers. So it understands that that's the sample space that you have to work with, which matches things like response time in practice. The only catch is that when you back translate what the model's predicting, any linear slope that you fit is actually going to be an exponential slope if you were to unlog the outcome and show how it's being predicted. If you can live with that, or maybe that's what you intended, then this is just fine. Yes, the trick is in limits, at least, to try and figure out how it's giving the parameterization of the model. So this is what it is in SAS. SAS was the only program, by the way, where I found log normal was possible as an option. So SAS Glimix is the only routine. I couldn't find it in Stata. I couldn't find it in R that gave me the same results. So logging it and then running a regular linear model may be a reasonable alternative in that case. Here's gamma, which is another one. I'm pretty sure there's an article on your reading list that is a tutorial on how to do gamma regression, as they called it. And this is another one where the gamma distribution doesn't have zeros in it, so it's just positive numbers, and it understands that the data can go forever into positive infinity. So you end up with these shape and scale parameters that work together to create the mean and the variance. But this is one where there is a separate parameter related to variance, and so it does a reasonably good job then at capturing that. So there's no like, the mean is supposed to be the variance, and it's only one parameter version of this. It already has two. And I think there's special cases where, like, if the scale is 1, then it becomes this distribution, and if the scale is 0, it becomes that distribution. I remember reading about that, but I don't remember what they are off the top of my head. So those are two that I know of that get used in that context. And then if you have zeros to add to it, then you'll have to do it as what is known as a two-part model. So two-part and hurdle are exactly the same ideas. The difference is that a two-part model, the part for how much is continuous, whereas in a hurdle, the part for how much is discrete. So if you have discrete data, you can pretend it's continuous, but if you have continuous data, you can't pretend it's discrete. So so for instance, an M+, which is a package we're going to start learning after break. And if you haven't done so already, make sure you have access to it in the virtual desktop. M+ has a two-part routine to it, where if you have a zero inflated outcome, there is code that you can use to cut it up inside the program, and it predicts the logit of whether you have a zero, and then the amount part that's continuous, and you can use a log residual distribution to that. So it will log it so that the continuous part allows for positive skewness if you want to. So, and in this case, we don't have to worry about zero truncation because it's usually paired with either log normal or gamma that doesn't have zeros. So it's just a true separation of if zero and then how much if not zero. All right, so there's your complete pile of zeros taxonomy and what the keywords would be to look at each of the possibilities. And in most cases, you can use, if it's a zero inflation model, you can use a likelihood ratio test to decide if you have extra zeros. If you decide to split it up into two, then you would want to keep both submodels no matter what. Okay, I think that's, yeah, software. So here's a full listing of where I found all the stuff across programs. Okay, so do you want to see an example? Why not, right? I made one. So there's that. Example 4b. I have those sorts of models first, and then I have quantile regression in this. So I stole these data from the Agresti book that's on your reading list, and we are predicting the house price for a house that's sold based on house characteristics. I have no idea if these data are real or not, but they look like they could be, so it's a reasonable example. So this is a data set of 100 homes as our unit of analysis, and the predictors that we're looking at are whether or not the house is brand new construction, the square footage. So in this case, I have made it square footage in hundreds of square feet and centered it at 1,500. So like my reference house would have 1,500 square feet. The number of bedrooms and the number of bathrooms. So this type of variable then, I've got a picture of it right here. This is what it looks like. So it's continuous in that it's prices that are in dollars, probably cents too. I can imagine if the negotiations did not go well, maybe we got down to like, I'll give you $100,006.35. Maybe the negotiations got down to that fine grain level. But this is a distribution where it's not obvious what to do with it. Like if I looked at this, I'd be like, well, can I pretend it's normal? And the question is, well, this is the marginal distribution. To what extent are these houses out here, which you would either call positive skewness or potentially outliers, to what extent are their prices sufficiently predicted by the characteristics of the house that we're putting in the model, such that in the conditional distribution, they would be reeled in and not as much of a problem? That's what I don't know until I fit the model. But here's a box plot. Remember those? I had to get this out back from intro stat. I haven't made one of these in like 15 years. So according to this, we have quite a few outliers, these very expensive houses, where most of the houses are down here around, 100,000, 150,000, and then there's these, rich people out here. So here's a question. It's like, well, do we want to keep the rich people houses in the sample? From the perspective of, well, yeah, somebody bought that house and that's how much they paid for it, like it's a valid observation, yes. But from the perspective of, well, what about leverage? We don't want those houses to like drag the regression line into weird places because they're so far away, and maybe we should throw out the outliers. Then no. But if you are going to do an outlier analysis like they do in some textbooks outside the context of a model, which is a terrible idea, where would you cut this off? So like here's a couple houses out here that are definitely sort of far away from the others. What about that one? What about that one? Where do the outliers start?
Around 350.
You got to vote for here? Yeah, like if this house wasn't here, I'd be inclined to say just these ones. But because it's here, I don't know. And this is exactly the problem. So outlier analysis is potentially problematic for two reasons. Number one is that if I just do it based on the original y and not the residual of y, then it makes no sense. Because the model assumptions are not about y. They're about what's left over in y after we fit the linear predictor. So there's no rule that says that I can't have these outlying observations in my marginal distribution. But then also, even if I found residual outliers, how much is too much? And there's an inherent subjectivity to that. And it makes it even worse if the analyst is like, well, what happens if I delete that house? Ooh, I like those results better. Let's go with that. Right, and that's the idea of forking paths or researcher degrees of freedom or p-hacking or all of those words that imply subjectivity that is potentially problematic. Question?
Well, we kind of talked about this in IoT, like if the model doesn't fit, like, do you remove questions, but then it can make things worse? Like, it doesn't always fit in the end, but I don't know, what about treating them as like two separate groups? But I guess if there isn't that many in the second group, it wouldn't.
Yeah, there's not enough. And so what I want to show you are options. This is a data set where I don't know what the right answer is, but here are some reasonable things that we can do, given that I have positive skewness and or outliers here. So this is the situation that we're working with. Here's all the usual stuff with respect to me making categories. So I only had a couple houses that had 5 bedrooms. So I decided to lump the houses that had 5 bedrooms with the ones that have 4. And so I made it 2 new variables so that the reference house has 3 bedrooms. And then I put in a predictor for whether they only have 2 instead of 3 or whether they have 4 instead of 3. So this is just based on sort of visual inspection of what I would have reasonable power to detect with the differences. Did the same thing with bathrooms. So most houses had 2 bathrooms. So I'm looking at that as the reference, and then what happens if they only have 1 versus if they have 3 or 4. Then we have square footage. I ended up having to make a quadratic version of square footage for a few reasons in some of the packages. And then I also made a log version of price to treat as an outcome to show the equivalence of the log normal model. So the usual data processing steps with respect to that in SAS, in Stata, and then in R. So take a quick look through that. I don't think there's anything in here that you haven't seen before with respect to that. So then we have just some code for data description, how to get the frequencies, marginal distributions, box plots, and things like that. So in every analysis in this handout, we're going to fit the same linear predictor. So I've got the reference house is not new construction. It has 3 bedrooms. It has 2 bathrooms. It has 1,500 square feet. So then the linear predictor dictates how house prices are going to vary as a function of whether it is new construction, whether it only has 2 bedrooms, whether it has 4 bedrooms instead, only 1 bathroom or 3 bathrooms instead. And then I put in quadratic square feet, thinking that the larger the house, the more it should sell for, but only up to a point, right? So more stops being worth more money in some kind of asymptotic way that I'm going to approximate with the quadratic trend. So what if I just did regular old linear regression? That's my first option. So just to remind you, this is more for pedagogy than anything else. When people say I did a regression, they mean I used an identity link function. Right? So there's nothing in the model that's going to keep the predicted houses from going negative. And I think that the residuals should be normal. So I put in all my predictors here. I added a contrast. So I'm asking for whether or not the model has a significant R-square, essentially, is how you can think of it. Whether the predicted Y from these predictors is significantly correlated with the original Y. In Stata, I'm using GLM. I'm doing it in maximum likelihood across all of these so that it's comparable with respect to the generalized models. And then I'm also using the V-factor thing in Stata so that the standard errors match what I get out of SAS. And let's see, where is Solomon? Are you here? Yes, you're here. I'm using your trick, Solomon, that he sent me. He figured out how to fix this. So in R, I'm using GLM. And he figured out that you are allowed to calculate a new variance term. So this is the residual variance divided by sample size rather than degrees of freedom. And you can feed in that new dispersion into a summary statistic to get results that match SAS. So hooray for that. Because when you're using maximum likelihood, it's supposed to use n and not n minus k for variance terms. And then the usual fit statistics here. And then GLHT, which doesn't work with the new dispersion trick. So the standard errors for that are consistent with the REML version instead of ML. But we're used to that problem by now. So here's what I end up with. A note to myself, this is the thing I screwed up before. This is the residual variance of house prices. This has nothing to do with fit. For the normal model, this statistic does not indicate anything. So the scale factor of the model is the version of the residual variance as estimated from maximum likelihood. Gradient column, everything looks e to the tiny number, so that is indicates we had no problems with estimation, as we might expect. So the reference house, according to this model, costs $128,000. If the house was new construction, it costs significantly more, so around $60,000 more. If it only had 2 bedrooms, it actually costs more, but not significantly. My guess is that those are condos. And they have things like pools and, views of the beach or something fun like that that might cancel out the bedrooms. If you have more bedrooms, it's not significant. If you have fewer bathrooms, it's not significant. More bathrooms is not significant. But I do have a linear effective square footage, which given the quadratic term is evaluated at 1,500 square feet specifically. So at that point, for every additional 100 square feet, it goes up $10,000. Now, it might be surprising that we have so many non-significant effects in here. At least it was to me. Because if you think about what makes a house cost more money, number of bedrooms, number of bathrooms, square footage, like all of those things come to mind. But here's the thing, like if your house is bigger, that likely means you have room for more bedrooms and more bathrooms. So everything that you learned in regression about collinearity and predictors being related to each other is still the case here. My guess is that these things are all knocking each other out because they're all symptoms of having a larger house for the most part. So it makes it more imperative than to look at sort of the overall R square of the model, which I didn't do here, but what we would normally do. How well do these things work together? They do create a significant R square in this case. So here's the Stata output. Everything is pretty much the same. The chi-square test agrees with that. And then here's the output from R. Here's the ML residual variance that we used in the summary, and to get a new version of that. And everything else is close, but not exact, I think. So now here's the question. These are my residuals. Normal enough or not? It's better. So some of the issues with the really spendy houses out here were reeled in. But if it were perfectly normal, the residuals would follow this line. And the other issue here potentially is homogeneity of variance. So like there's a lot more variance out here in the expensive predicted houses than there is over here. So this is I think, a good example of I'm not exactly sure what to do. I think there are formal tests for whether or not the residuals have a normal distribution, but they have issues. They tend to be overly, tend to flag more things as having problems than what, especially if you have larger sample sizes. So let me just show you some options as to what else one might do. Let's just log transform it. That's one thing I can do. So I can do that in Glimix. Hang on here. Log price. That's the difference. I'm still using identity link and a normal distribution. I'm just predicting the log of the price instead. So even though this is in Glimix, it's just a regular linear model, same as before. Same thing in Stata, and same thing in R. In SAS, I could also go to the trouble to fit a log normal distribution to it instead and predict original price. And literally, I get the exact same output either way. The likelihood is the same. The parameter estimates are the same. The standard errors are the same. Everything is exactly the same. So this is the one instance in which transforming your data is the same thing as fitting a generalized model. So now we have much smaller residual variance because we've changed the scale of the outcome, but everything else is, the patterns are the same. I won't say the coefficients are the same because they're predicting the log instead. So new construction still has a significant effect, as does linear effective square footage, but now we have a quadratic in here. And just as a review, I don't know if we've done that in this class, but you've probably done it with me before. This is conditional on x equals 0. So in this context, x equals 0 at 1,500 square feet. So at 1,500 square feet, for every additional 100 square feet, log price goes up significantly by 0.08. The quadratic, what it does to it is make that linear slope less positive. It slows it down. So it's like the slope is slowing down, and eventually, if you followed it long enough, would go the other way. And the rule to interpreting quadratic coefficients is to multiply them by 2. So twice the quadratic slope is how the linear slope changes per unit x. Because the value that's given there is actually half the rate of acceleration or deceleration in physics terms. So you have to multiply it by 2 to get to the full rate. So these two terms are working together to create a parabola, essentially, of how square footage relates to log house price. So some differences in the results there. And everything else is the same across the other programs. Here's gamma. So back to original price, and then dis equals gamma as an alternative. So this is one that it's a continuous distribution that allows for some positive skewness. And we're going with a log link in this case to keep the predicted house prices positive. In Stata, there is a gamma option within the GLM package. However, it doesn't do the same thing. I don't know what it does, but it doesn't match at all. So somebody fixed it. Again, some person wrote their own Stata thing, and it's called L gamma. And this gives us the same results as the other packages. So the only thing that it takes in L gamma are the predictors, and it will yell at you if you have C dot or I dot in front of them, by the way, in this routine. You're not allowed to use those features. So I had to take the C dots. Forgot to take them off here. This is a copy-paste error. I have to take them off here. And it does allow E-form, so you can unlog it to get odds ratios, no, incident rate ratios. That's what they're called in this case. And in R, it's the GLM package again. Family equals gamma with a capital G. Why? I don't know, but it wouldn't run otherwise. Again, that took me a few minutes. Why is it yelling at me? It says gamma, it says gamma. And then I channeled my inner Jonathan. That's a capital letter. Oh, that's why it's yelling at me. So we have a link equals log and family equals capital G gamma. And so then I think this is indicating, based on the fact that we're out of normal land, that there's actually less variance than the model expects. So this might be a case of under dispersion, but I'm not 100% certain on that. We end up with new construction no longer having a significant effect, but we still have the same pattern of the linear plus quadratic square footage. So we are seeing things a little bit different across the various options for this type of data. And scale factors in various forms. So it's labeled scale here, which is the variance multiplier in SAS. It's given as phi in Stata, and it also gives you as log phi, just for fun. And then it gives it to you here in R. That's the phi, but it's not quite the same number. So it's off just a little bit, just like everything else seems to be in R. And then here's the same conclusion with respect to the Pearson residuals. Looks like we have under dispersion. So all of these options that I've shown you so far are meant to address positive skewness, but they're not meant to address outliers. So I want to show you something that's meant to address outliers. So think back. This is what I'm going to show it to you next time. Don't worry, I know we're almost out of time. I can read the room, the Zoom room and the room, as it were. But do you remember back to intro stat? Like, put that hat back on, right? I was a freshman in college when I took intro stat, and we covered descriptive statistics and measures of central tendency. Do you remember those? There's 3. They all start with the letter M. What are they? Mean, median, mode. Yes, exactly. So everything that we've been working with in this class, and they say in most of statistics, is based on predicting the mean, right? The conditional mean. But if you have outliers or skewness, a more robust estimate of central tendency is the median, right? So why can't we just predict that instead? We can. I know. That's what quantile regression is for. And more specifically, not just can we predict the median. We get to a really cool picture. See, I'm going to leave you wanting more. We can predict all the percentiles. So this is where we're headed. What these pictures are showing is what the slope or the fixed effects would be if we were to predict any quantile in the distribution, any percentile. Because the median is the 50th. We can predict the 25th, we can predict the 75th, we could do anything we want. So this is a really, I think, not just useful for outliers, but useful if you have a hypothesis that's not about the mean. So like if you have a distribution, say, of response time, something like that, And some people are really fast and some people are really slow. It's a different question to ask, what predicts how slow you are amongst the slow people than what predicts how fast you are amongst the fast people? And one way to think about that is, how do I predict the 25th percentile? Those would be the fast people. How do I predict the 75th percentile? That'd be the slow people. So what this is plotting is how effective the predictors are at each point of the DV. So it's kind of like an interaction term with respect to the outcome rather than the predictors, which is sort of cool. So that's what we get to talk about, I think, next week. And by then, hopefully, I will have the multivariate stuff ready to go for Tuesday as well, since I can't make a whole class out of quantile regression. As much as I might try. So that'll be coming up next week. So any questions before we call it a Thursday? No? Fair enough. So then make sure you try to get your formative assessment done by Monday night if you can, please. Start working on your homework if you feel like it. Let me know if you need anything. Otherwise, have a good weekend. Enjoy yourselves. Take care of yourselves. Thanks for coming.